Okay, so previous homework assignment was to look at block expressions, right? Um, and so we were to add a block expression to our language, which allows for any number of no code or remember expressions. So we added some ways of expanding our environment and boils down to a list of results. So we gave an example down here where now you can have multiple lines of code where you might remember a couple of things. So when we say remember A equals 15, remember B equals 17, this spit out A is implemented, well, is executed in the environment that has been expanded twice by this guy. So, while this kind of, if you have a list of no code expressions, we might have an initial idea where we might say, hey, maybe we map the execute a no code expression function across all those with the current environment, which would be nice if we can do that. But the problem is that environment might be changing. So we need to recursively go through that list, making sure that we pass in the latest, greatest environment. Okay, so let's go and add, good.
If you had a let expression as one of the block expressions, that wouldn't apply to the let.
Correct. It would just be a local environment. Yeah, so what he asked is if one of your no code expressions was a let expression, the enhanced environment that lives inside of that let only would exist for the duration of the let. I think though that's not something we'd have to solve as a special case. Yeah. Because I think the only thing that we have now that changes the environment is a remember expression, right? So effectively, if it's a remember expression, we need to make sure we're passing in, we're catching the updated environment before we pass it in. And if it's anything else, we can just execute it in whatever our current environment is. Okay, so, and I gave an example of what a block expression might look like. Does anybody have a more creative syntax for a block expression other than just do a bunch of things? Well, that's not more creative. Well, it's actually less creative, especially in the context that you had this as a starting point. What'd you come up with? It's got to be better than that, even if you just go with silence.
I tacked on a pair of parentheses starting from the first remember all the way.
Oh, so you could just pass it the catter as the everything but the, okay, but what did you have as your first word? Okay, so not creative, but more creative than that. Okay. So we, no suggestions, we're just sticking with do, okay. No. do this. Or how about do dash all dash of dash these?
I like that.
Do all of these? I do kind of like. What's up? So we need to add this guy to our parser first.
I created a new parser interpreter for this, but I thought it was fun. I don't think I have to.
Well, so let's think about that. You created a new one just for this.
I don't really understand why.
Well, it comes down to what the grammar would look like for the language. If the grammar has to, so if we go back here and we add our new line to our grammar. So we're going to call this no code grammar continued. Somewhere in here, we're going to have a Do all of these. Followed by zero or more no expressions. No code expressions, right? Well, isn't a remember expression one of our no code expressions? Well, but that's important. So your question is you didn't really know when you should add another parser or not. It's not a coin flip situation. It's if we had a situation where it was either a remember expression or anything that's a no code expression. If remember expression was truly a special thing, then it would make sense potentially to have this in, well, no, we wouldn't have this in another grammar, but that would have been another parser, but that would have made sense for a remember to be in its own parser. Huh? Remember is in its own parser.
I think we decided that you can't do remember, you can't put a remember.
Okay, here's a remember expression parser, which means that we, oh, right, can't put a remember inside of a remember. So that means that one of our, in the grammar of no code expressions, a no code expression could be any of those things, or it can be a remember expression, but that's a different kind of animal. So because in a grammar, we are, this kind of goes down to, well, if we write the remember expression here, the idea would be this. I don't remember if we added it to our code, but inside of no code, one of the types of no code can be a remember expression. That's one of the forms of a no code expression is a, actually, was that going to be a true statement? In and of itself, that's not true, because then that would say, no, I think this is okay. Yeah. So we could say it can be a remember expression here. That's in our no code grammar. Then we would have our remember grammar. And our remember grammar would look like, we just had the word remember and then the symbol and then the value. This would be remember followed by symbol followed by a no code expression. So the reason why we put remember in its own grammar, which then means it's in its own parser, is because a remember expression is built in terms of a no code expression. And since you can't have a remember expression over here, that's like an illegal entry for it, we had to pull that guy out of no code because it doesn't fall into the category of no code. We have no way of saying, well, any no code expression except a remember expression. We can't say that. So that's the reason why we had a separate grammar for remember, so that we could describe remember correctly, which then meant why we had another parser for that guy. So then the question here is that when it comes to block, we say do all of these, and then we have zero or more no code expressions, or actually we would probably say something like this: no code or remember expression zero or more times. And I probably put all that in. So I don't like putting the parentheses there since it's not part of the syntax. So usually it's the formal syntax be written this way. It's this or this any number of times. All right, so a block expression allows for a remember expression as one of its special cases, or it allows anything that's a no code expression. Yes, which is why do all of these is part of the no code grammar. So that's all covered right there, right? That kind of answers the question. Does this need to be in its own parser? The answer is no. Since this guy suffices as a no code, where he can have a version of himself inside of himself, that's allowed to be part of the no code grammar. So he should be part of the no code grammar, and therefore he should be part of the no code parser. All right, that makes some sense. All right, so we're going to add this to our no code parser up here. Okay, and we'll say something like equal par no code do all of these if that's what I'm looking at. All right, then what am I going to output? Well, I'm going to output a list containing, maybe we call this do all of these expression, or actually we can call it a block expression in the parsed code. So we'll call this is a list containing, we can name these things like block exp to spell out expression. Exp, okay. So this will be a block expression followed by, now the rest of the stuff inside of this code is either going to be no expressions or remember expressions, right? So that means as I go through it, if it's a no expression, what do I want to do? I want to call parser, no parser on it. If it's a remember expression, I want to call remember parser on it. Make sense? So, and this is going to be a list of expressions that come in one of those two forms. But
I think we still have a way to, I think if you have things in the first expression, parser is still,
oh, because it is legal no code. Like that gets parsed by a remember parser. Okay, well that actually makes this easier then. Yep. So we will map no parser across the coder of no code, but now this is going to give us a list. So I want to append this list and what's returned by map there, passing the no parser function across all the elements of our current no code except for the word, or the, yeah, I guess the word do all of these. All right, so that should give us, I think, accurate parse code. If I go and I grab our sample code here, I'll update the syntax here in a second. Not run this guy yet. Let's just make sure it gets parsed correctly. So here's my block expression with the parsed version of all the crap inside of it. All right, so now this guy's ready to be cooked, ready to be executed, right? Oh, I need to get coffee. All right. So in our run parsed code, we can put it wherever we want in here. Let's do an EQ car parsed no code block expression. If I'm looking at one of those guys, that means I have a effectively I have a list of parsed no code. Well, I have a list of parsed things. Some of those things might be remember expressions. Some of those things might be no code expressions. So if it is a remember expression, I need to treat it as a special case because I'm going to get a new environment out of it, right? If it is a no code expression, just go to town, right? Just do its thing. All right. Now, I probably, well, I guess this would be a toss-up. We could make the argument that, hey, we can make predicates for our testing whether something is a no code expression or if something is a remember expression. Well, let me ask you this as a group. What would be the reason to create a predicate here? Remind me, what's a predicate? Okay, so so it's a function that takes in a parameter and boils down to true or false based on some circumstance, right? So what would be the argument why we might create a predicate to take in something and returns true if that is a no code expression, or false if it's not? Go ahead. Okay, tell me, what does that mean?
Like later on, if you did something that takes in a sort of expression, something you can have a predicate to figure out if it's expand the environment, and then right now we don't have to expand the environment.
Okay. Okay, so that's kind of maybe an argument for a like expand an environment thingy question mark, a predicate where you can pass it something that says whether or not this dude might change the environment. I think that makes some sense. Not kind of the direction I was going with that, but I think that's definitely a reasonable insight. Why else? What's the other advantage of putting, because otherwise what can I do in this particular situation? In this particular situation, I can ask, is it a remember expression? If it is, do one thing, else must be the other guy, right? So I can write it pretty easily here, but what would the what advantage would it give us to create the predicate? Or if you want to answer it the opposite way, what disadvantage do we have if we don't create a predicate here for checking specifically whether something's a no code expression? Go ahead. Well, we don't in this case because it's just going to be caught in our else, right? So as long, to your point, as long as we don't add something else that changes the global environment, I think we'd be covered if it's one or the other thing. But I think your point about expandability is a good one, because if we entertain the idea that we might eventually have something that we imagine that will also update the global environment, that guy would be allowed in here because we need to take that into consideration, because anything that changes the environment on this line, that environment's going to be the new environment on this line, and we have to handle that. Okay. There's kind of an obvious thing here that we're missing. Right now, we've picked a syntax, right? We've picked a syntax for our language. And this kind of goes down the path of assuming we add some more things in here where maybe we have 3 or 4 different grammars and this guy only accepts 2 of them. So if we start, so that else thing maybe doesn't necessarily, or maybe accepts 3 of them. So the else doesn't just work. We need to really be able to ask a question. Is it this kind or this kind or this kind? If we change our syntax, if we go and we decide, oh, well, I no longer want it to be a do mathy stuff. I want it to have a different name. I've updated to version 2.0 of my language, and we've decided that syntax wasn't stupid enough. So we need a more creative syntax, right? At that point, we now need to search through our code and find all the places where we made some assumptions about what some syntax might have been. As opposed to if we just had a predicate that says, are you one of these dudes? The only place we'd have to change our code is in the predicate for that, saying, are you one of these guys? That makes some sense. All right. Now, the downside to that, though, is if we're going to have that predicate, as of right now, we're imagining, okay, well, maybe we're not going to, at least at this point, we don't have to have more than an if else for this. The downside would be if we're going to have a predicate, we're going to use that predicate. That means every single time that we update our language, even adding a new ability to NoCode, we then need to go and toss that into the predicate. So now not only are we updating our parser and our interpreter, we're also updating the predicate to make sure it keeps up with the additions we're making to our language. Make sense? So we can certainly argue this all over the place. I think for now, let's just not go out of our way here to do something that's just going to just randomly just take time. So we'll do it as an if else in this case, which is not going to hurt anything. But I just want to make sure we do think about that. This kind of falls into that same category of, do you have a separate parser or not? As long as you've gone down the path, because this is one of those examples with this predicate, where we really could argue either way at this point in time. Do we waste time now or do we waste time later? Possibly wasting a bunch of time in the middle, right? So I don't think we're making a cop-out choice here. I think we're making a reasonable choice because at this point we have no plans of making this worse, let's say. But we definitely want to go through an exercise of thinking about what's the right step forward, or what's at least a reasonable step forward when we add something to our language. So we're at least making it based on an educated thought rather than just, coin flip. Do I create a new parser? We'll call that the Jason coin flip. Okay. See, now that was creative because it's based on an inside joke. That's what makes that creative, even though the name of it isn't creative. But block expression is not creative, which is a problem. It's just so later on, he's going to rage about this. I can tell. I hate all of you, mostly, and a little bit. Okay. So if we're in a block expression, we don't care about the car of it, right? The car of it just kind of was this placeholder. That's how we got into this little bucket here. So we really care about the rest of the stuff. So given that, the pattern I've been going through here is I've been kind of saying, let's throw this into a let so we can kind of label some stuff, especially as things start getting a little hairy. Sometimes you might bump into a situation where you've created a let where it wasn't all that complex, but I think it makes some sense here. I'll start it off as a let, even though I've kind of made the argument that, well, you can just make everything a let rack and that'll cover your bases, right? But let's use the right tool for the job. You don't go and get the power drill to screw in one of the little light switch cover things. You can use a normal screwdriver for that. So you create a let here, and we'll have our environment, and we're going to have a list of let's call this a list of legal expressions. Purposely spelling this out so we kind of remember what this meant for us, right? Because right now we have two kinds of legal expressions, and who knows, later on that might change. Because at the very least, we have this goal of not having hidden randomness in our code that we need to go back later on and look at the parsed version of code and figure out what the CADDDDDDDARDDD of something was, what we were actually extracting at that point. So this guy is going to be the car of the cooter of our parse NoCode. Cooter will be the list. You're right. Because this is going to be a list. So list of legal expressions is going to be everything except the word block expression. So now I have my list of stuff that I need to process through. And we actually are going to have this as a let rec here pretty shortly, but we'll leave it as a let for a moment. In fact, this might be our first opportunity where we're going to write a function inside of a let that calls itself recursively. So I imagine that's the path we're going down here, as opposed to a helper function. I'm guessing most of you probably wrote a helper function for it. So this would be a good exercise. But I promise you, what I'll have is the code you had in your helper function just stuck inside of a let rec. Okay. So list of legal expressions. Now our job in the body of this this part of the run parse code is to process through that list. And what we want to do is we want to process through that list in such a way that if I'm looking at a, I might actually still make this an external thing. We'll see. We'll see where we go. Okay, fine. I'll do it. If we're going through this, and every single time we have one of two situations. I'm either looking at an expression that's of type remember, right? And my parse code, what just pumps out the what is it? Remember exp. What do we get out of a remember expression? Here, I'm going to do one thing here. No, it's going to be a waste. So this guy is going to give me this word. So if I'm looking at something whose car is that, then I'm going to get a new environment. Okay. I'm lost. Where's my, oh, there's my interpreters. All right, so we'll put this in the body for, well, actually, we're going to still write our code here. I know this is where it's going, so we're just going to upgrade this to a let rec. So I'm going to write a function inside of here. So we're going to say process list is going to be a lambda that's going to take in that list as a parameter. And then it's going to ask the question, are you, well, it's going to do our normal pattern, right? We're processing through the list. If we're out of stuff, boil down to the empty list. So we'll have we'll do it in the cond. Null list, boil down to the empty list, because presumably our output here is going to be a list of results, right? So I'm going to be building a list, and what do we do to build a list? Probably a bunch of conses, con some stuff together. All right. So if I'm out of things to process, I'm going to just boil down to the empty list. That'll finish off. That's my finishing move for a series of conses. All right. Otherwise, if it is, so I'm going to say if the EQ car, the car of that guy is going to be the expression. So if the car of the car of list is that word, right? So the car of it's going to be the parsed expression. The car of that guy will be what kind of thing it is. So if the kind of thing that guy is a remember expression, then I know I'm going to be getting a new environment out of this guy. Make some sense? All right. So I'm going to just put some dots in here for right now. We'll come back to that in a second. Else, I must be dealing with a remember expression. And if I'm dealing with a remember expression, huh? Oh, thank you. Yeah, I must be dealing with a no code expression because I was either out of stuff, and remember our grammar says that a do all of these is either a no code expression or a remember expression. Those are the only two animals that are allowed in that list. So if it's not that kind of animal, it's got to be the other guy. Okay. And if it's got to be the other guy, we want to go ahead and execute him in the environment that we currently have. That makes some sense? So, and I'm actually going to have this guy take in a environment. We'll have them take in the current environment. We'll name it that. All right, so else we're going to go ahead and call, what is this guy called? Run parsed code. Well, we will cons the result of run parse code on the car of list and the curry NV we currently have on whatever process list. That's our inner function here. So we're in the process of defining process list instead of a let rec. So process list is effectively a helper function. He just happens to live inside of a let. So I'm allowed, by calling it let rec, I'm allowed to now call the function that I'm in the middle of writing inside of him. It allows for recursion to work. So I'll call process list on the cooter of my list, as well as my most up-to-date environment. Because this particular line didn't change my environment, right? Okay. And then let me finish writing this. So if I'm in this let rec and I have my list of legal expressions, what am I going to do? I'm going to process that list. What list? My list of legal expressions in my starting environment that I had right there. So I'm going to call the function that I just wrote, passing it the parameter or the local variable that I created there, which is everything except the block word. And then I'm going to pass it the starting environment to start doing this in. All right. And the starting environment is going to be the environment that we have at this point in time. Okay. And that will be everything for block expression with the exception of this magic here. All right. So if I'm in this case, I must be looking at a remember expression. We do need to run that remember expression. But when we run a remember expression, what's the result? I hope we wrote it this way. The result should be an environment, right? It gives us the updated environment. What do we call it? Do we call it like run remember or something? No, we couldn't have written it that way. Oh, because it's got the We did write it that way, just as a catch-all. But, I don't like that. Do I like that? Oh, it has to work that way because we're calling our code initially with so this is okay. It makes our grammar correct. The grammars we've written, it makes those accurate. We don't really have a workaround since when we first run our program way down here, run this guy right here, the run parse code, I have to give it what I got, right? And now we know we have some new kinds of languages that might be mixed up in there. Well, so that means that this dude here has to handle it. He doesn't have a choice. Whether we would want him to handle it or not, we got to have a starting point, right? Now, you could maybe write an intermediate thing here that kind of plays quarterback, kind of hands it off to the right runtime. I think that would probably be overkill for what we're doing right here. But the reason why I'm not necessarily a huge fan of this is that this interpreter here should mimic our grammar for our NoCode, the NoCode or no code language or whatever we called it, should mimic that grammar. And in this case, it almost mimics the grammar. We got this extra little dude here that doesn't really belong. And we immediately say, oh, wait a minute, you belong somewhere else. And we pass him off. Okay, so we're handling it in here, but at a glance, if you are, and this wouldn't, you don't want your code to necessarily be your documentation. So this isn't a deal breaker type thing. But if you were looking at this interpreter and saying, oh, well, this is following our grammar for no code expressions, and all of a sudden you bump into something that wasn't found on the grammar, that could be a little bit confusing. All right, but it's not a problem in this case because we are ultimately running our parse remember expression, which we could call directly. In fact, I feel like I might even just want to call it directly rather than passing it back through here just because you can. I think I do want to do that. Like, why pass it through something else if you already know where it needs to go? So if I'm in this part of the COM where I'm saying I'm looking at a remember expression, well, I'm going to call this guy on the car of our list. And that guy is going to give me a new environment. Right? This is going to boil down to an updated environment. In fact, just to be verbose with this, just because, let's create a let. And we'll make an updated environment, which is the result of calling that guy. And then once we have our updated environment, so I mean, we've processed that line now, right? We have a new environment with the extra variable added to it from this remember expression that we had right there. I've stored that updated environment in this guy right here. So now what I'm going to go ahead and do is I'm going to call ProcessList on the rest of my list. Oh, sorry. ProcessList on the rest of my list, along with this guy takes an updated environment, the current environment it should be working on. So I'll pass him that updated environment. Okay, so if I'm looking at a remember expression, go ahead and process it. Remember the environment that was the result. Then call ProcessList with the rest of that list, everything but the guy you just processed, passing it now the environment that you just updated. Go ahead. this guy. And my current env is current env. Thank you. He was saying that this function here that we wrote needs the expression you want to run, as well as the environment in which you want to run it. Hence the idea of environment passing interpreters. Okay, so I'll process the list, the rest of the list in this newly updated environment that was the result of this guy. So then it'll come back through, go to the next guy. In this particular case, we'll get another updated environment because we had two variables we defined at the beginning. Then we'll get into the else, we'll cons, run parse code on the first thing inside of the cur env, which is the parameter being passed in the process list. So one thing we need to be careful of is we need to keep track of which environment is which environment here, right? Because we have several things floating around. The cur env is the local parameter of process list, which is the current environment in which we should be running stuff. But we will talk about a possible problem that'll come out of this in a minute. Well, I'll probably ask you about it. But so cur env is the environment in which we should be running things inside of here. When we are updating our environment, when we're dealing with a remember expression, I'm creating a more local variable called updatedEnv that I'll use to pass into my next call to process list. So updated via env will become the next cur env, that next recursive call through. Okay, so there's my end of my let rec. There's that guy. I think that should do it. Let's see what we broke. A domestic fight down the hall. Then we're going to run. What did I say the answer of this should be? 15, 17, 32, because we're going to remember, we're remembering A equals 15, B equals 17. We'll spit out A, we'll spit out B. So that's our 15, 17. And then we'll do some mathy stuff on A and B, and then spit out and storing the result inside of C. And then we'll spit out C. $15 to the screen, 17 to the screen, 32 to the screen. Does that thing solve it? Okay. What's the problem? Well, I'll just ask it generically like that. Do we see any weaknesses in our code right now? Problems with our language? Limitations that our language might give us? It's perfect. It's not. So what we see anything? Technically, as I have my grammar written. Oh, go ahead.
Well, to your point, like, technically, it's without- what if I would use this screen?
No, I'm talking about, let's assume that what we've done right now is correct. Forget about, like, you know, these, I mean, I think this is as good of anything that says, look, this was just printed to the screen. I'm saying, do we have limitations now in our language, what we are allowed to do? Our grammar currently for NoCode dictates that we can have any of these things as legal NoCode, right? And one of those things is a block expression, or whatever we called it. So therefore, would it be legal for me to have a block expression inside of a block expression? Was it? Well, oh yeah. So the answer would be yes. It would be legal.
I think no.
Okay, tell me why.
I just think that.
Is it? Don't you do it all the time? Sure you do. You've never written a function before that had a for loop inside of it? Or a for loop that has another for loop inside of it? Anytime you see opening, closing curly braces, isn't that a block expression? It's a list of expressions. And can't you put a for loop inside of another for loop? Okay, so you've doubled down. You want to go in with a triple down now, or do you start seeing you're seeing the cracks in your armor? Okay, so go ahead. All along. But were you with me because you understood it or because you were oblivious? Either way is acceptable and better than him. Okay. Yeah, so I mean, block expressions are ways for us to have collections of expressions that we want to execute in a certain order. But we do have to ask the question, are we allowed to have them inside of other ones? Now, you could make the argument in your language does not have to adhere to our, you might say, look, you can't have a block expression inside of another block expression. Why? Because I said so. Deal. Now you solve the problem in terms of the constraints the language gives you. Okay, but if we assume that we're trying to write something that kind of mimics languages that we're already familiar with, a block expression inside of a block expression might make some sense, especially if we think ahead a little bit. And instead of viewing this as a generic block expression that just says, here's just some stuff, do these in this order. Why would I want to have that when I could just have the contents of that in my first block? But it's not that hard for us to extrapolate and say, well, we might have a loop type thing in our language that would have its own block expression as part of it, and possibly its own scope, right? Its own new variable environment that doesn't necessarily affect the guy outside of this. Go ahead. We don't have any way to get back to the global environment. Oh, right. So the idea is this. What we have right now is we don't have a way of, let's see, do I had a block expression inside of one of the block expressions, then that would change the global environment, or would change the oh, like, so if inside of a, let's just write it. So if inside of this guy, we had another do all of these. And all we did in here is remember A is actually 13. Something like that. So presumably this A is equal to 13. Well, we can actually really have the argument about this. Assuming this is something we might want to write, we can think of this as like a let expression, where it's like, look, you're trying to modify the expression. So from this point forward, A is 13. If that's the case, this works as is, right? But if we say, look, when you hit the end of this block expression, anything that you changed inside of here was part of the scope that was with that original block expression. And now you need to revert back to what you had before. So presumably when we hit the end of the do all of these for this guy, and we changed A to 13 and then did nothing with it, and then this guy ended, that modified environment should now revert back to A is actually still 15 for the rest of this block expression. But as we have it written right now, it's not going to do that. We're going to get what, a 30 out of this? Hold on, I might have written this funky. Do all of these. Is that because of how my append works? Yeah, I saw. But I'm wondering, is that because I kind of recall we did that from our scope? At least I thought we did. We ran into another do all of these, and what do we do with the do all of these? We boil down to a list. Oh, no, this is correct. It's in a weird order. I mean, this is the correct output of this block expression. If I throw another spit out A in here, then it would have one thing in it. Remembering it doesn't have any result.
So it is already happening.
Yeah, but I'm trying to figure out why. I mean, the result is you're right. So when I call do all of these, and I'm calling it with the current environment. Yeah. Well, yeah, that's because that's the result of my cons. So inside of what he's talking about is, where are we at here? This is my process list function, and this guy is building this list. So when I ask, is the list I'm currently working with, are we done processing stuff? Yes, there's my empty list, which will finish off all these conses. Yeah, so when we had an empty list here before, it was correct. It was correct because inside of my inner do all of these, when I didn't spit it out, the result of the do all these was nothing. It was correct to have the empty list. But what I don't like in here is I'm remembering something, that I'm doing a bunch of stuff. Oh, and then spitting it out here. I spit this out. Well, I'm not spitting it out currently, but I'll put it back where I do spit it out. So I actually do spit out the 13 before I go and do the rest of these things. So this is in the correct order. So I spit out the 13. Oh, so well, but about presumably we definitely had it here. Let's just follow it. When I hit the end of the do all of these, that means I've hit the end of my lost. Where's my code for? Here it is. I've hit the end of this guy, so it returns the empty list. I only had my updated environment when I was in there. So then I came back around and I was now operating off of the current environment from the previous call to it. So I did revert back to my environment. So we actually accidentally still have this working. And what did it is recursion, right? This guy finished when I stopped making recursive calls, right? So he was only as good as the updated environment he kept passing around. So when he ended, his updated environment was done. The previous unconnected call to ProcessList that was in action as we were going through our original block expression. So I'll kind of explain it with, so when I'm in here, we're in, we'll call this ProcessList 1 and ProcessList 2. ProcessList 2 is the guy who's processing our inner block expression. So we're inside of ProcessList 1, which has an environment. We're inside of ProcessList 1, which has an environment. Now we make a call to ProcessList 2. So now our most local environment is ProcessList 2's environment, but he lives inside of ProcessList 1's environment. So this guy does everything from the most local, all variables boil down to the most local environment. It does it from the perspective of Process 2's environment. But as soon as this ends, Process 2 is now dead. So now we are back into the most local environment being Process 1's environment. Process 1's environment, so on and so forth. All right, that makes some sense? Okay, but now let's break it, because what I was saying before still is a problem. So I'm going to take the do all of these. Let's see. Do I have a way of writing legal code that will do this? Well, let me show you what I want to do. And then we can figure out how if we have a way of legally writing this in our language. We'll still see that this would be a problem, presuming I have a way of writing this in my language. Or maybe the way to write it in my language would be I want to have something along the lines of that, where I have a block expression all within itself, followed by another block expression. Well, but then if we have a block expression of block expressions, we just saw that that will work. Well, will work is in the eye of the beholder, right? Because we saw that each block expression will create its new environment, then die off afterwards, right? But if we, can you give me an example in Java when you have a block expression that does not disappear at the end of its execution? I already gave you one where it does, right? Anything you created as a local variable inside of a for loop dies when that for loop's gone. Yeah, while loop. So if you defined a variable inside of a while loop, that variable is part of the global environment, not part of a local environment of the while loop. Yet they're both block expressions. Let me just, I want to make sure that that's a true statement. If I actually define it inside of there, before we just make the assumption that that's how the languages work. I'm pretty confident, but, huh? Yeah, I can just do it in here. We'll do it in C++. So we're going to say int b is equal to 5, C out b, while I is less than 3, its c is equal to I, C out C, I plus plus, C out C. So I define C inside of this block expression. Is it still alive after this block expression ends? I think it will be. Where if I had done this in a for loop, it would not have been. Actually, maybe it would have been in a for loop. Because I think it's only the stuff I define up here. We'll test it with a for loop too in a second. So I believe the output here will be a 5. Then it'll be a, oh, I need to set this guy to a 1. Then it'll be a 1, a 2, and then it'll be a 3. It was not declaring the scope, this guy right here. So it did die with this scope. And then I'm presuming if I replace this with a 4, int I is equal to 1, I is less than 3, I plus plus, basically the same logic, but part of a for loop. C would also not be defined. Okay. Yeah, so anything that was done inside of this block expression did die before we got out to the next block expression. So our code does mimic this. Yeah, so the idea here would be, should our language support a block expression followed by a block expression? And does a language like C or C++, does that support it? No, because even if I put 2 for loops in here, for int I is equal to 1, I is less than 10, I plus plus, do something in that block expression. And then I have a completely separate block expression. Let's just say it happens to do the same thing, doesn't matter. But this is a block expression followed by another block expression. Does our code currently allow for something like this? It does, because we're inside of a block expression. So this is a block expression that contains an expression, an expression, an expression that is a block expression, another expression that is a block expression, which might have their own expressions inside of there. So I think our code already works for the way that a block expression should work. All right, that makes some sense. Yes, that's kind of a fun one. Okay, so let me copy all that. Okay, so next on the docket, just so we make sure we have enough time in the course to get to it, and we'll probably revert back and start thinking about loops and things like that. Let's think about object orientedness. It's called object-oriented languages. All right, what differentiates? I mean, right now I think it's fair for us to say that we have now created something that loosely qualifies as a procedural language in a functional language, because now we have block expressions, right? I can say do this, then this, then this, then this, even though that's a very recent addition that we have to our language. This is the first time we've kind of, well, I want to say broke away from Scheme, but Scheme does have an equivalent of this with called a begin expression, where you can have a block of things. But for our intents and purposes, we can say that we now have something that functions as a procedural language. Remind me, what's the difference between a procedural language and an object-oriented language? When we first learned about this from me, we did it in terms of the procedural telephone versus the object-oriented telephone. Yep. Yep. So if you walked up here and I had something here that I said, this is a phone. It's a big pile of wires, but you come up and you investigate it and you eventually determine, oh yeah, that is a phone. Didn't look like one, but it is one. As opposed to an object-oriented version of a phone, looks like a phone, and you believe it will be a phone, but this is no more of a phone than that guy was. He just happens to look like a phone, and he's way more convenient to hand to somebody instead of shoving this pile of wires, right? Okay, so what's the purpose of an object-oriented language? Why did we invent them? Why wasn't procedural languages? Why weren't they just good enough? Why is that a problem? We're programmers. It's supposed to look impossible. In fact, we probably lost a little job security. Because now, grandma can pass a phone to somebody. Is grandma going to know what to do with a pile of wires? Is she going to know how to fix the pile of wires? So why do it? Okay. Humans do like convenience. That's probably a reasonable enough answer. One of the purposes of a programming language is to allow us to solve problems in a similar way to how we already solve problems, right? Well, in real life, if somebody asks you for the phone, you hand them a phone. And to you, a phone looks like this. It does not look like a pile of wires. You would need to be convinced into thinking that that was a phone. And that's probably not a phone you try to hand to somebody, okay? So older languages, these procedural languages, they stopped making as much sense to us once we started solving harder and harder problems with our programming languages, which came with the advent of computers getting faster and faster. And I like to make this correlation with kind of what's happening in the world right now. If we go back to when desktop computers were first becoming like a thing, like an actual thing, let's call it like 1990, something like that, where it was not uncommon for you to walk into Well, even 1990, it might have been somewhat uncommon, but we'll just use 1990 as our example. It would not have been uncommon for you to walk into a dentist's office and them have a computer behind the desk. And that would have been a newfangled thing to many people. Before that, they just had filing cabinets with, you know, paper folders in it with your records and stuff like that they had taken, right? They didn't have these computers that were storing stuff. But now in those early days, those computers did not do nearly as much as they do today. Today, your doctor probably does not have a physical file with your stuff in it, right? Or if they, well, I think that's probably a true statement. They might have some physical things they printed out, but only on that day. Because if you like need a copy of your x-rays, you know, you have to like request that, like wait a week for them to actually like print them onto, onto something so you can take it to another doctor. And actually even now, I haven't transferred my x-rays in years. Now they probably just do it electronically, right? Who's your new doctor? We'll send over your x-rays. And it's no longer something they're mailing them, right? They get a, you know, a digital copy of the stuff, and that has to be transferred with, you know, this thing called HIPAA compliance for security purposes and stuff. But, you know, point is everything's digital now. Go ahead. Potentially. I mean, that is not unfounded today, but would be rare today. You know, we almost think if a place says, oh, you're the only way to submit this is to fax it to us, you kind of roll your eyes like, okay, well, where can I go to find a fax machine? Right? So that still exists, but it almost doesn't exist anymore. We're right on the cusp of that. So if you go back to 1990, and computers were just starting to find a commonplace in the world, right? And then you look at those computers compared to today's computers, our computers today are way more powerful, right? And part of what's driven us wanting to make them more powerful is because the things that we were trying to do with them kept becoming more and more. And this is where human invention comes in, right? We saw the same thing with like Apple's App Store. When Apple's App Store came out, you know, a lot of people don't necessarily remember when the first year the iPhone was out, there was no App Store. You just had Apple's stuff on there. You had Safari and the YouTube app was on there, but you know, you had a very limited number of apps that were pre-built into the phone. So we were at the mercy of the stuff that Apple could come up with and write. Now you might say Apple comes up with interesting enough stuff and things like that, but even as creative as they might be, they're not going to be as creative as bringing in 10 million developers and say, hey, come up with your own ideas and start doing stuff. Maybe Apple wouldn't have come up with Angry Birds, right? They probably wouldn't have come up with the fart app, right? that was a big hit in the early days of the App Store. But in any case, as more and more people started doing stuff, our innovation started growing and we started coming with new ways of using apps. Now we're using apps for all sorts of things, just like computers started finding new uses and we started taking the limitations of the capabilities of the computer. And then what did we do? We went and made them faster, right? So you had this thing that was driving that innovation, and our computers kept getting faster and faster and faster. And the types of problems we were solving with the computers kept getting more and more complex. Well, that's why we needed an upgrade to our language types, because the old language types, while fine for the problems we were solving up to that point, were starting to become inconvenient because we were solving problems that were becoming more and more like the problems we solve in real life, rather than kind of these, I don't know, cliche kind of applications that were just like, oh, this is what a computer can do. They were actually useful applications. And I personally believe we're going to start seeing some of the same stuff come out of virtual reality. Now that it's become more consumer mainstream. You know, 4 years ago was $4,000 to even play. You know, now it's $300 and you're playing. Well, it's going to keep getting cheaper and cheaper and cheaper and smaller and smaller and smaller. And we're going to see all sorts of applications that come out that we can't even think about today. That we're like, oh, I didn't even think VR, I didn't think that was a thing. But it's going to be kind of a cool thing. All right, so we'll come back on Tuesday and we'll start, we'll say start here. What makes an object-oriented language, and object-oriented language. All right, questions, comments, concerns, bribes? All right, I'll see everybody on Tuesday.